Hello. Hey, all right. Thank you so much for the introduction. Yes, my name is Cem Yuksel again, and talk that I'm going to give you is about my paper on high performance polynomial root finding for graphics. Yes, that sounds like a name constructed for HPG, and that is true. But if I told you high performance polynomial root finding, you would probably tell me, oh yeah, we need it for graphics, right? Because we really deal with polynomials everywhere in graphics. And but the thing is, we try to avoid sort of more complicated, more higher order polynomials. We try to stick with simpler polynomials because, well, they're cheaper. Now, I'm going to tell you how you can solve all sorts of polynomials much higher order than we typically do, and we can actually have pretty good performance with them. So that's going to be the whole topic of this talk. All right, let's start with quadratics. We love quadratics because we know the solution for it from grade school, right? The quadratic formula, you plug it in, you get your result. So we love them. But don't use that directly. Just use the slight variant I mentioned in the paper that is numerically a little bit better. But quadratics are super cheap, super easy. You just compute a square root and you do a division or two. So nothing, to be honest, will compete with the performance of quadratics. Quadratics are special. They're super fast, right? But unfortunately, not all problems we have end up being quadratics. Sometimes we need to deal with higher order polynomials like cubics. And cubics appear actually a lot in computer graphics. I think one of the most common use cases for cubics in high performance applications is continuous collision detection. So when you have a triangle and a vertex, you need to solve a cubic to find out when they are coplanar. So this is used in games and all sorts of physics-based simulations a lot, so they appear a lot. How about higher order polynomials? Degree 4, degree 5. Well, there aren't that many examples of those because those are considerably more expensive to solve. Actually, I know one paper that attempts to actually solves degree 5 polynomial. It's they're using an existing polynomial solver out of the box, and that's about an order of magnitude slower than the one that I'm going to present today. So it can be quite a bit expensive. How about going further? Degree 6, 7, 8, 9, 10, 10. Are you crazy? Yeah, like this is like crazy town. Like who would in their right mind think that in a high performance application, I can just go and solve an order 10 degree 10 polynomial? That would be crazy. And that's exactly what I'm going to show you as an example. We're going to look at a tube like this and compute ray intersections with that tube. And that's going to come to a degree 4 polynomial. Sorry, degree 10 polynomial. And the details are in the paper. But I'm getting ahead of myself. Let's get rid of that. Here's the thing. I'm going to tell you how to solve these and more, actually. But I'm going to do that without telling you anything that you don't already know. So this is going to be really simple stuff. We're just going to combine some existing ideas together in the right order, and we will have a high-performance polynomial root finder. So that's pretty much the reason why I actually attempted to write this paper. I wanted to write this paper because I thought, hey, I wish I knew about this before. That would have saved me a lot of time and energy. So hopefully, by the end of this talk, you will be happy to use any polynomial. When you run into a polynomial, you'll say, oh yeah, I know how to solve it, and that's going to be super easy. All right, so that's the idea. But let's start with cubics. All right, cubic polynomials. Now, I avoided cubic polynomials like the plague for a long time, but I could not avoid them forever. Actually, that was here when I was dealing with my curves, my curve formulation. Some of these actually required solving a cubic polynomial. I could not avoid it, but it was a specialized problem. I knew that there was always a solution, and there was always one solution. So what I did in that case is that within the range, I used bisection. Don't do that. Very bad idea. Bisection is terrible, right? Don't. If I can say only one good thing about bisection, that would be that it works. And I'm not sure if it is good, because if it didn't work, we would probably move to the next solution, which would be so much better. So don't use bisection. And the reason why I'm saying that is that, like bisection, here's my interval that I'm interested in. and I know that there's a root. With bisection, I'll just split it down the middle and see that, oh, my root is contained in this part of the region, so I can get rid of the other part. So with all that computation, I received exactly equivalence of 1 bit worth of information. That's it. So for the next bit, I need to do this again. This is really inefficient. We can do much better. How, you ask, we can do much better? Well, we could use Newton iterations. Actually, that's what I would suggest that we use. And Newton iterations are not that more difficult to compute either. Like, just instead of just computing the polynomial, you also compute its derivative. And when you're dealing with cubics, this derivative is a quadratic, very easy to compute. So that gives you your next guess, and you iterate until you converge, right? The problem with Newton iterations is that they are notoriously unstable. To make them stable and to make sure that they always work, here's a trick. You combine Newton iterations with bisection. And when you do that, you have a stable solution that always works. Hopefully, you mostly use Newton iterations and use bisection only Newton iterations when only Newton iterations fail. I actually describe exactly how to do that in detail in the paper, but I'm not going to get into that. It's actually fairly easy to do. And the solution that I describe also satisfies a given error bound. So this is numerical iteration, right? So you're going to have an error bound. And I talk about how to make sure that your error bound is satisfied as well. All right. But unfortunately, this is not what I did the first time. I had to actually solve cubics properly, not with bisection. I realized that, oh, wait, there's an analytical solution. How about we just implement the analytical solution? That works, actually. It works just fine, but you need to solve a cubic root and some trigonometric functions. That is expensive, right? And it's not just that they're expensive. These operations are expensive. It's also, they are sort of, especially this cubic root, I presume they are implemented as numerical solvers. So instead of doing numerical iterations on this cubic root here, I could just do numerical iterations on my actual polynomial. And with that, I actually would get much better accuracy. So the accuracy of this analytical solution, unfortunately, is not that great. So not recommended at all. It's slow and not very accurate. Jim Blinn has a much better solution, I would say. It's actually comes down to something similar. It's using similar sort of formulations. So same type of computation. It's actually a little bit more because it's using homogeneous coordinates. So it becomes a little bit more involved computation-wise. But the accuracy is much better. So it definitely improves the accuracy. Performance, not so much. So we want high performance, right? So it'd be much better just to do numerical iterations ourselves in our own problem. But the problem there is that this gives me only one root. These would give me all of the roots. I want all of the roots. For a lot of problems that I have, I need all of the roots. So how do I do that? Very, very easy. So give me a cubic. Here's what I'm going to do. Super simple trick. Are you ready? I'm going to take this cubic, and I'm going to split it into 3 pieces. Exactly at these critical points where its derivative is 0. Its derivative is a quadratic. I can very easily solve that quadratic, right? Super cheap. And I can find these critical points super easily. And then I have 3 pieces of my polynomial. And let's say this is my interval that I'm interested in. I can easily split my polynomial into 3 pieces. And if I have roots in these 3 pieces, I can find them using numerical root finding, with combining Newton and bisection, right? That's as simple as that, right? And it works. It's great. And there's a really important benefit here. If any of these pieces do not contain a root, like the blue one in this case, I can easily see that before doing any numerical root finding. Because you see that both endpoints are below 0. That means I cannot have any root in here, right? So I don't even have to do any numerical root finding here. In fact, I can do one step better. If I find one of these roots, let's say that I find this red one over here and call it XR. If I find one of these roots, then I can use deflation. So deflation would take a cubic polynomial like this, and with a known root that I've already computed, I can write this cubic as a product of x minus xr and a quadratic, right? And the coefficients of this quadratic they're very easy to compute using the known coefficients of the cubic and my known root. And with that, I'm left with a quadratic to solve now. So if I can find one of the roots, the other 2 roots, if I have any, I can find them very easily, very cheaply by solving a quadratic. So that is the solution that I would recommend for cubics. That is, you split the cubic into 3 pieces by solving a quadratic that is going to be its derivative, and then find the one of the roots, using Newton iterations plus bisection, so it's guaranteed to converge to the root. And then you deflate the polynomial using the one root that you found, and finally find the other 2 roots using the deflated polynomial, deflated quadratic. That's it, and it works brilliantly. It works just fine. So cubics are no problem. How about higher order polynomials? Can we do that for polynomials of degree 4 plus? Well, give me a polynomial of degree 4. What I'm going to do in this case is actually very similar. I'm going to take this and split it into 4 pieces. And I can do that by finding its critical points. Those critical points will be the 0 crossings of its derivative. Its derivative is a cubic. We just talked about how to solve cubics. So if I can solve a cubic, I can solve a quadratic in the same way. And if there are any roots in any one of these pieces, I can very easily find them using the same numerical root finding, right? And hopefully one of them is in the interval that I'm interested in, I can find that root easily. If I have a degree 5 polynomial, I can do the same, split it into 5 pieces in this case by solving a quartic degree 4 polynomial. So for higher order polynomials, this is the algorithm, right? Give me a polynomial. I will first solve the 0 crossings of its derivative. That's going to be a polynomial of 1 lower degree. And with that, I'm going to have a bunch of intervals. And for each one of these intervals, I'm going to look at the endpoints of the intervals, the value of the polynomial at the endpoints of the interval. If the sign of these endpoints are the same, then I cannot have a root. If they're different, then I definitely do have a root. And I can find that root using numerical root finding with combination of bisection and Newton iterations. One important note here. Now, if you look at this algorithm, in terms of its computational complexity, it's quadratic, right? Because for solving a polynomial of particular degree, you need to solve a polynomial of 1 lower degree first. But if you add deflation to this, just like we did for cubics, you get an algorithm with exponential complexity. So don't do that. It's great for cubics. For higher order polynomials, it's not great. I believe theoretically, in some cases, for quartics, for 4th order polynomials, it will still pay off, but in practice, I've found that it gets slower. So don't use deflation here for higher order. All right, let's look at computation times. Right, I told you high performance. Let's see if it actually is. So here's the cubics. I'm comparing 2 versions of our solver here. One with some lower accuracy using a larger error threshold and higher accuracy. Now this yellow one is matching the accuracy of the analytical solution, and this red one is matching the accuracy of Blind's version, right? So you should compare them in terms of performance that way. I also added the regular Newton iterations here, although this just finds one of the roots, and it's not great. So, but one funny thing here, if you look at it, you see that this doesn't make much sense, right? I mean, we're using Newton iterations for these. How come Newton iterations on their own slower? That doesn't make any sense. Well, here's what's happening. The problem with just blindly applying Newton iterations is that when there's no root, you don't know, right? You need to iterate, and then the iteration never converges, actually bounces back and forth. And at some point, you give up when you reach the maximum number of iterations. So like you need to do a lot of computation to figure out that you don't have a root. But when you do have a root, actually, Newton iterations are a little bit faster because they don't have the overhead of our splitting and other steps. Also, this is somewhat deceiving because in my experiments, about 30% of the time, these regular Newton iterations could not even find that one root. So it might be a little bit faster, but it doesn't even work. So don't even bother with it, right? Don't use it. Split first, do our version. Don't even bother with this, right? And you see that on average, it's better in terms of both accuracy and performance from the analytical solvers. All right, this is the average condition here. You see, it's significantly better, I would say. And if you compare this to quadratics degree 2 polynomials, you'll see that degree 2 is quite a bit faster. I'm saying less than 10 nanoseconds for this particular hardware that I tested on the CPU. But it can be, actually, I think it's about 8 nanoseconds. But I also have an optimized, hand-optimized SIMD implementation that brings it down to about 4 nanoseconds on that hardware. So it can be significantly faster, right? Cubics are going to be more expensive. What happens when we go to degree 4? Actually, well, it goes more than doubles. Yeah, because to be able to solve at degree 4, I need to solve degree 3 first. For degree 5, it goes a little less than double. And for degree 6, okay, it's it's increasing, but not that much. Actually, we should probably stop here, or maybe even before, because degree 7 polynomial, I have 32 bits. I can't even properly compute the polynomial itself with good accuracy. So root finding for degree 7 polynomial for 32 bits, don't do that. That's probably not a good idea. So let's move on to 64 bits. That's a much better idea. For 64 bits, I'm showing you the performance results on a graph or up to degree 10. As you can see, they're increasing sort of quadratically, but it doesn't look that bad, right? It's pretty good. Actually, the computation time depends on the error threshold you pick, right? So if you pick a smaller error threshold, of course, you're going to have to do more computation. But if you compare this to an out-of-the-box popular polynomial root finder that it's used everywhere, you'll see that now our poly in this case is sort of off the charts. That also should not give you the wrong impression. Actually, this algorithm will catch up at some point. In my experiments, about degree 20 to 30, they start, our poly becomes a little bit faster, actually. So, but for low degree lower polynomial degrees, it's actually, the solution is so much faster. Okay, I keep saying fast and fast. Let's put this in context with a challenge. The challenge that I picked for that is hair rendering. I'll tell you why I picked that challenge in a little bit. So for hair rendering, we have a curve, let's say a cubic curve, and I'm going to have a circle that defines the size of the hair, forming I move this circle around and forming a tube like this, and I'm going to find ray intersections with this tube, which ends up being a polynomial of degree 10. So I need to find the roots of this degree 10 polynomial. So for this problem, we're going to use our brute force polynomial root finder and see how well it does. Well, how am I going to know if it does well? The reason why I picked this problem is that actually there exists an excellent high-performance solution for this problem in the form of phantom ray hair intersector. So we're going to see how these two solutions compare and see if we can get anywhere close to it, right? So we're going to do hair render, but we're not going to do shading and all and everything. We just want to do ray intersections. So we're going to render something boring like this, right? And let's see what the results look like. For cubics, the actual numbers don't matter. So I'm going to show you the relative numbers. For brute force polynomial root finder, let's say it's 1x, right? Solving a degree 10 polynomial. If this is 1x, then phantom ray hair intersector in this case gives me 1.3x. So it's actually even faster. Yeah, about 30% faster. So that's great. Now, I can do more, actually. I can take these curves and make them longer by combining multiple curves into just one larger curve, like 5 times longer. If I do that, actually, phantom ray hair intersector does not like it so much. So its performance comparatively, that goes down quite a bit more. If I take this cubic and use a quadratic approximation of these cubics. So we had a paper at HPG a few years back about how to convert cubic curves to quadratic curves and how to approximate them. So if you do that, then we get a lower order polynomial. Because we get a lower order polynomial, this becomes so much faster, and in comparison, we get quite a bit more speed up. But of course, this is just one hair model. If you have a more straight hair model, phantom ray hair intersector does a little bit better. So these numbers don't matter that much, I would say. But in the end, the point that I'm trying to make is that we get something out of the box that is sort of can be compared with a high-performance solution to this problem. So that this tells me that this polynomial root finder is actually giving us really good performance, right? So that was the whole point. Actually, I got to thank here to Alex Rashido. He ran these my implementation and compared with his sort of more optimized implementation, put in ++ here, and got these results. As you can see, if you keep splitting these curves and get shorter and shorter and shorter curves, Phantom ray hair intersector actually comparatively does a little bit better. With the original curves, maybe polynomial root finder might be a little bit better. So, there's the point is not to say that this is faster than phantom ray intersector. That's not the point. The point is that we get a solution that we could even compete with and highly optimize dedicated solution for this problem out of the box just by solving a polynomial. So that tells me this polynomial solution is high performance. So if you want to test it and see how well it does in your own applications, just go to my website, X Polynomials, and you will find all the documentation and the paper and everything. And I have a source code. This is in C++. Just works like this. This is the entire code actually works. So you can solve it, in this case, a degree 5 polynomial like this. So just go and try it out. It's very easy to use, and see how well it does for your own problems, right? All right. With this, I would like to thank Alex first for wonderful feedback he gave me. Actually, that was really amazing, and also many others who gave me feedback along the ways for the earlier versions of this work. And I got to specifically thank the HPG, IPC, and reviewers who reviewed this paper. I had one of the best reviews I've ever received in my career. So if you guys are not submitting your papers to HPG, you're missing out. I would highly recommend it. This was really amazing. Now, I would like people to know about this because I think this is an important deal. I wish somebody told me that I could solve polynomials much earlier. So I would like to extend this idea and spread it as much as possible. Because of that, I'm also going to give a talk at SIGGRAPH this year. It's just a talk. So this is the title. I've already recorded the talk a few weeks ago, I guess. So it's already pre-recorded. I guess you'll be able to see it in a little bit. So with that, I'd like to stop here. And I think that you guys will be able to take
Thank you, Cem, for the very lively presentation here. It was fun watching.
Thank you.
We have a bit of time for questions. There is already one on the question boards. Can you read this? It's about interval arithmetic and Toth's approach.
I would appreciate if you could please read them for me, because I'm standing a little far from my monitor.
Absolutely. So the top question, I think they're both related. I'm just going to read the top is, I was also going to bring up interval and affine methods. I imagine they would be slower in most cases, but there might be robustness advantages. The Toth approach is essentially bisection using interval arithmetic. Does that tell you anything?
Bisection using interval arithmetic. Are you talking about regular Palsy or something? I've experimented with quite a few different numerical root finders. And you will see some of these results in the paper. I've included some of them in the supplemental document as well. You will see that they all perform poorly in comparison to Newton. Actually, there's a special case. One special case, really crazy special case, for cubic, if all three roots are exactly at the same point, in that case, bisection performs a little bit faster than Newton iterations. But that case alone, in all other cases, actually, Newton iterations perform much better than everything else I've tested, including some higher order solvers. With higher order solvers, you can actually get fewer iterations. You can actually find a root with fewer iterations. You can solve a quadratic at each Newton iteration. And that reduces the number of iterations, but it increases the total computation time. So it didn't really help. So I tried all sorts of things, and I really converged on the Newton iterations in the end.
Okay, thanks. There's one question on the mic by Simon, if you want to ask your question directly.
Yes, sorry. I posted the original question about Toth. It was a paper I based some ray tracing on 32 years ago. So it's what if I remember correctly, and it's again stretch my memory. As far as I remember, Toth was used to find if the derivative was safe. Well, you could use it for basically creating a bounding box around your patch or whatever. So first of all, you could do AABB messes, but then it also, I think, you used on the first derivative to decide whether your Newton iteration would be well behaved. So at that point, you launched into Newton, and he got there very quickly. So it wasn't just bisection by any means. So I was just wondering if you'd seen it and tried it.
But that sounds like a very similar idea to me. So that's what I was trying to say early on in the talk, that, you know, this, I'm not going to tell you anything new, because these are just ideas that have been out there, but we just didn't know that if you put them together in the right order, you get a good solution for even higher order polynomials. So that sounds like the fun thing was similar idea to me.
The fun thing was that we were using revolution, so we're doing sines and cosines. So we weren't just polynomials. You could use any sort of smooth function in there. It just might be worthwhile having a look at it. I mean, God knows how old it is, but
thanks for the clarifications and for the pointer.
Yeah, okay.
In the interest of time, I think